So hi everyone, hope all of you are doing well. I'm a PhD student in IBS Center for Climate Physics. So my name is Arjun. I'm gonna present some of my results regarding how the mean and extreme precipitations within atmospheric river change in response to greenhouse warming. So let's okay. So let's start with the bigger picture here. So this is a global mean precipitation from era 5 reanalysis. So these precipitation systems can be separated into various precipitation regimes. So there will be a convective regime along the equator. There's orographic precipitation controlled by orography along high mountains. And again, then there's precipitation, which is driven by cyclonic or frontal systems. So it is this region that I'm going to concentrate on this talk. So if you look closely, these regions is characterized by strong precipitation over warm western regions of ocean basin, and this precipitation system seems to extend from southwest to northeast, following the storm track activity, as we all know. And these systems also tend to give strong precipitations over coastlines where these where there's storm track activity meets the land. So the classical way of looking at these precipitation systems is, for example, I'm showing an example of a system here. So you have precipitation systems over here, the associated cyclonic circulations, and there will be frontal activity associated with those cyclones, and which lead to precipitation. And here I'm going to propose a little bit alternative way of looking at these precipitation systems, which is through atmospheric rivers. So qualitatively, atmospheric rivers are defined as narrow regions of strong water vapor transport. So here in figure A and B, the dashed contours indicate the atmospheric rivers. So if you look at figure A, which shows the precipitation, so you can see that this precipitation system, many large-scale precipitation and strong precipitations happen within atmospheric rivers. And figure B is what it used to detect atmospheric rivers, which is integrated water vapor transport, which is nothing but the total water vapor transport from surface to the 300 hectopascals. So the figure B is used to detect atmospheric rivers. And in figure A, you see that these strong precipitation systems are within atmospheric river boundaries. So quantitatively, we detect atmospheric rivers as regions of strong maxima or local ridges. And I won't be elaborating much on the atmospheric river detection technique, but you have to assume that I detect atmospheric rivers correctly. And so last slide we saw some snapshot. So even if you look at the mean precipitation, so here the figure shows the contribution of AR precipitation to the total annual mean precipitation. So over the extratropical region, especially over the storm track, you see that up to more than 40% on average of the precipitation is contributed by atmospheric river-like structures. So not just in the mean contribution, even if you look at extreme precipitations, you see that ARs play a significant role. So here, the figure indicates the total number of extreme precipitation events divided by total number of extreme precipitations within atmospheric river-like structures divided by total number of extreme precipitation events. Here I define extreme precipitation as the 95th percentile of the daily mean precipitation for that corresponding month. So yeah, you see that 60% of the extreme precipitations over the extratropical region are within atmospheric rivers. Now that we know all these stuff about how atmospheric rivers influence extratropical precipitations. Here are my questions. So first one is to identify the hotspots where atmospheric river causes large-scale precipitation or extreme precipitation events. And secondly, how does the mean and extreme precipitations within atmospheric rivers scale with air frequency, like atmospheric river frequency and atmospheric river strength? And thirdly, see if we can identify some physical mechanism to understand these changes. So before that, I've used, for this study, I've used 25 kilometer high resolution CSM simulation. We simulated it for 3 scenarios: present climate, which is a CO2 concentration of 367 parts per million, and a double CO2 concentration and a quadruple CO2 concentration. All 3 of these simulations are run until equilibrium, approximate equilibrium, and then the last 20 years is used for the analysis. And again, the method used is a bit more sophisticated, so I'm not explaining this. Again, you have to assume that the detection method does well. And to prove that, I'm showing the mean atmospheric river frequency in A and B, and the contribution of atmospheric river precipitation to annual mean precipitation. So figure A is made from CSM high resolution run, and B is from ERA 5. So you see that both A and B is a pretty good match. So is D and E. Although there is a slight shift towards polar region in the CSM run, but however, it's a very good match. And to see whether the method is right, we have compared it with the other atmospheric river detection methods, which our method seems to be within the range of other methods. So once we done that, so I'm gonna answer my first question: what are the hotspots for extreme atmospheric river precipitations? So here, what I've shown here is the probability of an atmospheric river to cause extreme precipitation. Now I've calculated it as like this. So number of extreme precipitation events within atmospheric rivers divided by total number of atmospheric rivers. So is a extreme precipitation normalized by the number of atmospheric rivers. And now you see that all these regions where we know atmospheric river cause huge flooding, so like California region in the US, Greenland, which tend to have massive rain events recently, similar to atmospheric rivers, and also where Andes and Antarctica. So all these regions pops out, especially where this storm track activity meets coastline. So again, the extreme precipitation is defined using the 95th percentile of daily mean precipitation for the corresponding month for the present day simulation of the CSM. And now we see how it changes in response to greenhouse warming. And we see here that there's a significant forward shift in the probability of AR to cause extreme precipitation. So with greenhouse warming, we expect AR to cause large-scale extreme precipitation events in the polar, or etc., more toward the polar regions. And so this is the extreme precipitation changes. Now looking at the mean changes, you see again the significant forward shift in the atmospheric river frequency. So A and B shows the changes in atmospheric river frequency in response to double CO2, that is A, and quadruple CO2, that's B conditions. And similarly, we have plotted here is a contribution of AR precipitation to annual mean precipitation, and for 2 times CO2 in C and 4 times CO2 in D, and it's the significant regions. And now, from a global perspective, let's go into individual ARs. So if you plot the distribution of ARs, you see that the mean and maximum values of whatever for transport, which is kind of we used as a measure of AR strength increases by 14 and 33% in response to increased greenhouse gas content. However, we see that the mean precipitation changes are limited to 3% and 9%, which is much smaller than the changes in the AR strength. And maximum AR precipitation increases in a similar scale as mean AR strength. To illustrate this point more, I'm showing simple linear regression between mean AR strength and mean precipitation and maximum precipitation. You see that for a particular scenario, for individual scenarios, AR precipitation increases with AR strength. However, when you go to various scenarios, like from present day to increased greenhouse gas condition, this relationship weakens for mean precipitation. However, it stays constant for maximum precipitation. So to understand why there's a difference in the scaling, we started looking at the convection within atmospheric rivers. And we see that in general, the strength of convection, which is I've denoted characterized the strength of convection as a omega L, which is the mean vertical velocity from 800 to 500 hectopascals in between that region. So you see that there is a 5% and a 10% reduction in lower omega L strength in like double and quadruple CO2 condition. So that means on an average within an atmospheric river, the upward velocity reduces. And also here we see that the ratio of convective area to total area also reduces. So that would mean that in general, within an AR, the mean convection is less. And however, this convection happens through a much smaller region than present climate. So we hypothesize that the increase in heavy precipitation, probably due to the we have transporting larger moisture is transported through much smaller region, which leads to heavier precipitative events. However, when you take an average, the precipitation changes are much smaller. And so here are my conclusion. So mainly air frequency, precipitation, and probability to induce extreme precipitation events overall we have seen increase and a poleward shift. And now AR strength scales very well with maximum precipitation. However, mean precipitation shows much less much weaker relationship with mean AR strength, which we believe is due to reduction in overall convection in the atmospheric rivers and the reduction in the area of the overall convection within atmospheric rivers. And that's it. Thank you for your attention.